and how it is different from cache coherence, why you need them, and also synchronization. So all these things are actually are relevant only when we are talking about parallel processing, like writing multi-threaded applications. If you're not asking a
Yes, sir.
question,
Right,
can you
sir.
please mute?
Thank you, sir.
Thank you, everyone.
If you're not asking a question, can you please mute? I can hear background noises. Okay, thank you. Uh, Yeah, so remember all of this is related only when we are talking about multi-threaded applications, so parallel applications, right? So now the question is, the first question that we want to tackle is that I guess you just heard about cache coherence and how memory consistency models are different from cache coherence. Now take a look at this simplistic pseudocode of two-thread multi-threaded applications. I think uh, you can actually understand what is the purpose of this code. There is this variable a, and there is a particular flag, and you're updating it from the thread 0 running on code 0. You're updating that value, setting a flag, and the thread 1 running on code 1 is essentially waiting on that flag. So it is loading the flag and seeing if this flag is still not set, then it is looping. There is a loop here, and once this flag is set, it actually tries to read the updated data that is written in A into this register R2. So that I think pretty obvious from what is the purpose of this two-threaded applications, why application writer has written it. Now the problem here is that what that the value that you want this register active to have after execution of this code is 1, right? Because you have set it to 1. But the problem is cache coherence says nothing about it. It doesn't guarantee that. What cache coherence tells you is that, okay, for a given address, you would get the up-to-date value, like what is the latest value. Doesn't say anything about when different addresses are actually involved and which one should become visible before the other when there are two different addresses. Here a and flag 1, these two are different addresses. So it might so happen coherence doesn't forbid you from the fact that you can actually read value 0 here. It just may be that flag is updated value is shown to the thread running on the C1 before the updated value of A. So that can happen, and coherence will not stop you because it only talks about the for each different locations. But sometimes it's not uncommon for multi-threaded applications to write code where semantically two addresses are actually involved. Here, although these two, A and flag, these two are different addresses, but you are trying to use them together to semantically achieve something that is one thing that is like, okay, you want to wait on the flag before you want to actually read the address A. Now that is why the memory consistency model comes in. Memory consistency model talks about in what are the orders in which the load stores to different locations. A and flag, these two are not same address, could become visible to all other threads, means to everyone. To define it a little bit more, a memory consistency model actually specifies global order of writes to all memory locations, not a single memory location, relative to each other. Okay. And at the end, why it is needed is that it talks about, what are the ordering that are actually quote of load store that are actually legal, okay, for a given memory consistency model, so that you can reason about correctness of a multi-threaded program running on a platform that supports a given memory consistency model. So now there is not like there is one memory consistency model that is actually used by everybody. It depends from processor to processor, and that is trade-off. Typically, the trade-off is that the memory consistency model, which are also called the stricter models, that actually makes writing multi-threaded program easier. That also actually limits performance optimizations in the hardware, which means that it can make things easily programmable, but at the cost of performance. On the other hand, more relaxed models, put more burden on the programmer that he or she has to be more careful when writing multi-threaded programs that are actually error-free, but they might actually allow the hardware to uh, do more optimization. We'll talk about some of this, and as I say, like this difference on the processor to processor type rather. It's part of the instruction set architecture. So x86, which means that the processor offered by AMD or Intel, they have generally stricter memory consistency model. But if you compare to say IBM Power or ARM processors, they have more relaxed memory consistency model. So we'll talk about this. So there is not a one right memory consistency model. It's all about trade-off. Okay. So now let's get back to with that background. Let's get back to the problem, example that we were taking. So um, this particular piece of multi-threaded program would always return this R2 equals to like 1. That is the value that you want, like from the semantics of this application, if the memory consistency model guarantees that you know even if there are updates to different addresses, if you do not allow reordering of those updates when they become visible to all other cores or all other threads, then this particular program will work fine. Okay, if this condition is violated, for example, if this this update to the flag really can become visible to other cores, um, before this update to A1, then this program will actually may not return you the desired results. And you see, I mentioned may not because by luck you can still get the right results, because it just happens that okay, even in some execution this one the ordering was actually same, but it will not actually guarantee. So it might actually happen your program might run fine sometime, it might fail sometime else, which makes it actually really harder to debug. So memory consistency models and understanding that is very important for writing correct, quote unquote correct multi-threaded program. And parallel programmers rely on the memory consistency model to reason about correctness of their program. Now, as I mentioned, there are many different types of memory consistency model. So we'll start by talking about the most most intuitive but strictest memory consistency model called sequential memory consistency model. This is most programmer friendly, but it is also limits performance optimization. Okay. Then we'll actually talk about how a slightly more relaxed memory consistency model called total store order. It also called processor consistency model. It is less restrictive than sequential consistency, which means that it will allow more performance optimization in the hardware. This is something Intel or AMD's processors actually support, but at the cost of some programmability. Then we'll quickly touch, hopefully we'll have time, about more what we call the weaker memory consistency model, where it allows more and more performance optimizations, but it asks more from the programmer to write correct program. So there is a trade-off, and this is something that ARM and IBM power processors actually implement. And sometimes, just a quick anecdote, like sometimes you would actually hear these things like, okay, you have a program written in for Intel or AMD processors. run fine, but you need to now, so you want to target that software for, say, ARM processor. Now you might actually imagine that this is not, may not be a hard problem as such, because you can write cross compilers that can take the same program and convert using the ARM's instruction set architecture, right? Instructions. Now this problem is actually simple if you just consider a single-threaded application. But as soon as you go to multi-threaded application, the problem becomes tough because of the difference in the memory consistency model. So some programs that were earlier running fine on x86 may or may not run fine on ARM because because of its relaxed memory consistency model, the programmer needed to introduce more instructions, different synchronization instruction. We'll talk about some of that later. But the compilers may not be that smart to figure out why it might need to actually be more cautious, and that's why the reliability of the program can be can be an issue even if you actually cross compile some application from x86 to ARM processor if it is a multi-threaded application. Okay, that's the reason that memory consistency models are so important. With that background, we'll start with what we mean by sequential consistency model. It's the most intuitive, programmer friendly. And let's start with the definition of that. And then we'll slowly go to more relaxed models. So the idea of the sequential memory consistency model is very simple. So think about the shared memory that all these multi-threaded, all the threads of the multi-threaded applications are trying to access as a single thing, and it at any point of time it can take, say, update from one of the threads, not more than one. So basically what would actually happen, what it requires is that execution from a sequentially consistent processor should be such that there would be a global order of writes to any memory location. Okay, and in that global order, the load stores from each thread should appear in the program order. That's the requirement. So what is a program order? So whenever you write a program, it is actually compiled and it is actually presented to the processor. So there is a sequential stream of instructions that is presented to that particular code. And that order is called the program order. So basically, whatever that is actually presented to the hardware or each core, that is what for each thread. That is what its program order is. So what it actually sequential consistency says is that what you need to do is that the execution should be such that you should be able to create a global order of basically load stores to any location from any thread. There should be a global order for that. And in that global order, the load store from each thread should appear in the same order as the program order in those threads. So just let's take an example. Let us assume that there are two threads that are running of the same application that are running on two cores. Okay, so there is some store, and we ignored the all other non-memory instruction because they do not actually has anything to do with the memory consistency model. This is about the memory instructions, load stores. So let us assume that this is set of stores and the loads that are coming from the thread T1 that is running on C1, port C1, and there is this another set of load stores from the same application, but it's different thread that are running on port C2. Now, sequential consistency doesn't mean that there will be only one specific order of load stores. There can be multiple sequentially consistent order. For example, one of the global order could be like this. So this, it is like you executed store A from the thread T1 first, then you executed the stored A from the C2, then you executed something from the the C1, again executed something from the stored C from the the C2 core C2. Now this is a sequentially consistent ordering, because you can actually see first of all there is a global order, and in that global order the order in which that each thread's load stores are coming, that is same as the order within its each thread. That's the program order. Okay. Another possible order that is also could be sequentially consistent could be this, where these two instructions from C1 appeared first, then the two instructions from the C2 gets done in the memory, and so on. So here also this is also global sequential consistent, because if you look at this, again there is a global order of all load stores, and in that these instruction from each thread appeared in the same program, in the program order that of each of these threads. So this is a sequential consistency. So remember one thing, when we are talking about memory consistency model, we are talking about load stores that are coming from each thread and their program order. Okay, so but it will actually impact how the this multi-threaded applications actually behave. For example, let's go back to our example here. Now, if the system is sequentially consistent, you can quickly see that uh, uh, this value R2 that will be loaded into R2, it will always have to be 1. Okay, and the reason is that in the global order you have specified that a update to the A1 has to happen before the update to the flag 1, and it's a global order, which means that seen by all the threads, right? So that's a requirement for sequentially consistent. So if this another thread running on C1 actually sees this updated value of this flag, because it is actually looping here, then it is certain that the updated value of the A should also be visible to C1, because that has to have happened in the globally visible order, right? So what we can actually see, cache coherent said nothing about whether the value, that is the intended value of in the R2 after execution of this application, should be 1. But once you say that, okay, the system is also sequentially consistent, then because of the requirement of sequential consistent memory consistency model, it is guaranteed, then it becomes guaranteed that this will always return, R2 will always contain the value 1. Now, how do you specify these or the requirements of this different memory consistency model? For simplicity, the way to actually specify is to look at this kind of a table. What actually tells you the table, we'll read it soon, is that what kind of reordering between load stores to different addresses are allowed. So let's see what it actually says. So um, this means, say there is an earlier load operation, okay, from a given processor, and there is a later load operation in the program order. Means say there is two loads to say value, say address A, and another is address B. It says that this later load cannot appear to have happened before the earlier load in the memory subsystem. So what it says is that irrespective of the fact that for each given processor, each given core, there can be load stored to different addresses. They cannot bypass each other. That's completely restricted. So later load or store operation cannot seem to have happened in the global memory before the earlier load or store operation, even if they are two completely unrelated addresses, right? So that's the requirement it actually poses. And remember that these requirements are for each core. If each core makes sure there's no reordering of load stores from its code is happening even to the different addresses, you will automatically abide by this requirement of sequential consistency memory model. Okay, so let's take some examples to clarify this. So let us assume that there is two variable x and y, and initially their value was both x and y was 0, and we have two simple pieces of code. Load x, you do thread 0 first, do actually load x, and it actually it does load y. The code 1 does store y first. Remember that this order is different, and x store to x equals to 1 later. Okay, now the question is whether this load can return 1 while this load to y can return 0 or not. Anyone? Do you think if the system is sequential consistent, can this load to x return 1, but this returns 0? Can this happen?
No, sir.
Why?
Because in the core one, the instructions will be executed in order. So first y will be 1, then x will be 1.
True, because if you have seen the updated value of x, you are have to see the updated value of y. So it can actually return 0, 0, or it can return 1, 1. Those two are all legal by sequential consistency. But 1, 0 is not legal. So you can actually see that any kind of memory consistency model is not only for sequential consistent. It doesn't mean that there is a definite values that it would actually return, because multi-threaded programs by definition are non-deterministic. Okay, you know, it doesn't make it deterministic. What it actually does is that it makes few of the ordering illegal, and it allows the the parent programmer to understand, like, if or reason if their program is written correctly, it's properly synchronized with respect to a given memory consistency model. A program that is actually correct with respect to a sequential memory consistency model may not be correct compared to, say, total store ordering, TSO, because relax. Similarly, that's the reason we are coming back again, like something written for x86's TSO model may fall apart, may not be correct when you actually try to ship it to ARM. Okay, so this is an example. Let's so take another example. Okay, now the question is that can both this load x and load y can both return 0? If you assume sequential consistency. Someone?
Both can't return 0 at once.
Yeah, it won't be. So the way to actually check is this simple thing you can actually play. You put an arrow from from the earlier instruction to the later instruction here and here, because that actually signifies the program order. And then you put an arrow for causality, right? Like if you have to get 0 value, then this load should have happened before this store. So put an arrow here. Okay. Now, if you have to get 0 for this load, you have to put an causality arrow because this has to happen before the store to 1. Put an arrow here. Once you do that, if you find there is a cycle, then you know that that particular combination is not possible. So if you put those arrows, you can actually do a pen and paper and see there is a there will be a cycle. So that's how that's the trick to check if some values are possible or not. Okay, moving on. So the sequential consistency model is makes life of a multi-threaded programmer easy because it would behave the way that most of you intuitively want. But the problem with this is that it really restricts the performance optimization, particularly like many of this out of order memory level parallelism thing, right? Like, okay, what you have to do basically is that you have to wait for each load store to actually have happened in the cache subsystem. Means that you got all the coherence permissions and so on. It is done to the caches, then only the next one can happen, even though they can be two different addresses. So that's a problem that will limit your memory level parallelism. Means like it will limit performance, and no commercial processor today actually implement sequential consistency. They implement something more relaxed, and we'll actually go towards that, and we'll talk about why that is needed. So before we go into that, we want to talk about something called a write buffer. Okay, so this is not the store buffer. So what can actually happen is that you execute what's the purpose of write buffer is this. So you can actually execute load stores. You can actually commit them. Remember that you have to commit them in order and so on. But what can you actually do is that typically when there are actually load instructions, they are in the critical path of the execution, because why you would actually load some value, probably you do some compute on that, right? And until you actually got that value, the compute that you will actually use that loaded value can't progress. On the other hand, stores typically signify that some computation has happened and now you're writing the results to the memory, which can be off the critical path, because that store can happen in the background. You might not actually need that updated value immediately, right? So to take advantage of that, one of the tricks that the hardware typically processor like to play is to put a write buffer. So what it is, once a store commits, it will actually put that store updated value in the write buffer. Okay, at that point, the cache may not have the coherence permission, cache coherence permission to do the write to the cache subsystem. So it's not really completed from the perspective of the other processors or global memory that you have, but it has completed from the perspective of the core that is actually issuing it. So what is the advantage then? Then what you can do is that instead of like stores, maybe there is a store to A, then after that load to B. That load to B doesn't have to wait for store to A to complete. It can actually push the store to A to write, write buffer, and the load to A can actually go on and check the caches. It might actually miss in the L1 cache, can go to the L2 cache, L3 cache. It doesn't matter, right? So this load doesn't have to wait for an earlier store, which is to a different address, because semantically, for if you just consider that particular core and particular thread, that is perfectly fine to do. And if it is a single threaded program, for example, this is perfectly fine thing to do. Now the problem is existence of a write buffer will break the sequential consistency. So let's take an example. Okay, remember that we just said that for this application, this piece of code, this store to one, you just said that okay, now both these x and y cannot load 0, 0. We are originally assuming that the initial value of x and y is 0, and then in a sequential consistency should not. If you follow that, then it should not happen that this program, this multi-threaded program, can return 0 0 for both this x and y, the load to x and y. But the argument will show here that if you have a write buffer, the way we describe, this would not be guaranteed anymore. So let's assume that the store to y happens first. Okay, that goes to the write buffer. Remember that permissions are not there, so you will actually stick it to the write buffer. Then core one also does its write. It's also get into the write buffer. It hasn't actually happened in the cache subsystem. That actually starts from this portion. And then the load X happens, it can go to the cache subsystem and read the older value, because this actually hasn't happened in the global memory, and return 0. And you can actually see what can actually happen here. Also, it can actually bypass this. This y hasn't happened. Y equals to 1 hasn't happened in the memory subsystem. So it's going actually return 0. And this is a coherent system. It's cache coherence, by the way. But you can still get value 0 0. So write buffer basically breaks sequential consistency model. But then the designer, chip designer said this is too restrictive, right? And this will not allow a lot of a simple performance optimization like having a write buffer. So they said okay, let's change the memory consistency model then. As I said, there is no single right or wrong memory consistency model. It's about trade-off. So what this they actually came up with is called the total store order. So remember that for the sequential consistency, this that table that we had that told us what load store to of course to different addresses can be reordered, and there was no reordering allowed. However, here what the table is saying, a later load in the program order to an can bypass an earlier store as long as they are two different addresses. If they are to the same addresses, cache coherence takes control. There is no discussion about it. You can't, right? But if you are to different addresses, then a later load can bypass earlier store. If that happens, then if that is what you say, that is you advertise as your processor vendor, that's my memory consistency model, then the write buffer is fine, right? Because you declared it that I'm not, this might actually happen, that for each given processor, they later load in the program order can, as long as they are to the different addresses, they can bypass earlier store, while the earlier store hasn't happened to the global memory to be visible to all other thread yet. So that is the model that broadly x86 processors follow. And this model is also called total store order, because you can see still that store to store bypassing is still not possible. So that's why it's a total order on the store still remains. What it means is that you can have a write buffer, but that write buffer will be fast in, fast out. It will be a queue, because you can still can't reorder the writes to different addresses. Why it could have been useful? It could happen that, okay, store to A and there is another one store to B that is coming later, but the store to B, which is later, might have the corresponding cache block in the L1 cache. Store to A might be missed in all the levels of caches, where TSO would not allow you to bypass each other and make the store to be complete while the store to A is still hanging on into the write buffer. That won't be allowed by the total store ordering, because there is a no here in this box. Okay, so, and remember, I keep on saying it, that we are talking about this reordering and so on with respect to different addresses only. As soon as it becomes same address, it's coherence. Okay, we are talking about different addresses, then only you do this kind of optimization, and memory consistency model comes in. And also remember, these are specified per core basis. It just says the beauty of the memory consistency model is that although we are talking about parallel programming, But these constraints that you are actually, the reordering constraints you are specifying, it is for each code basis. As long as you stick to this requirement for each code, you would actually follow this table. You will actually follow that memory consistency model. Okay, so we already talked about this is one of the most popular memory consistency model. And why so? We'll take an example. Okay. Okay, this is something that we have already talked about. What the the optimization TSO will allow that is not possible in sequential consistency model. It's the existence of that write buffer or FIFO write buffer. Okay, let's take an example. Like so, we say that some of the programs will break. Now the question for you. Okay, so now under TSO, would you get the desired expected result where R2 is loaded with 1? Someone? What do you think? So you know that under sequential consistency, you will always get R2 equals to 1. What about now, TSO? We relaxed one condition that later load can bypass earlier stores as long as they are two different addresses. What do you think? Someone? Speak up. Like, don't worry. There is like, participation is more important. That's how we learn together.
A can be 0 because both the loads can bypass the stores, right?
No. How? So remember that these things that we are talking about, this is per core basis. Okay. So what the TSO says, the TSO would not allow this store to flag 1 bypass store to A. That won't happen. And load to load reordering is not allowed. Right? Are you there? Like, what's your name?
Srinati.
Okay, so you see the see the requirement. Like, this program would work as expected in TSO as well, because in the global memory order, that is means that visible to everyone. The TSO would not allow this update to A. Update to flag become visible before update to A, because
Right, the stores will still be.
Exactly.
Okay.
But also in the load also, here also this we have not allowed, like load to load bypassing is not allowed too. So which means that these two loads, they are loading to different addresses, but it cannot happen that as if that this load to A was executed before the load to flag. That won't be allowed either. So this program will work as it is. So you can actually see that some of the programs where you require this semantics, this will still work fine under TSO. Okay, now let's take in another example. So here, remember the same example. Here we said that under sequential consistency, X, both these values returning to 0 is not possible, right? Now, would that be possible under TSO? What do you think?
Yes, sir, it is possible, right?
Why you think so? Say your name.
My name is Surya, sir.
Surya. Yeah. Why you think so?
So because now store and load can be interchanged.
Yeah. So Surya is right, because now we said like we will think about each of the cores, right? And our table said that okay, there is a later load, and these two are different addresses. So later load can bypass, which means like as if they have happened before the store to Y. This can go up essentially. This can go up. right? And then you would actually get x and y equals to 0. So what it means is that there will be certain programs where the sequential consistency and the TSO will behave differently. It's not that all programs. And why TSO is popular is that, first of all, that it does an important optimization that we talked about. That it allows fight for a write buffer. At the same time, only some conditions, maybe this condition is not so important, but that flag one is of course important, right? Because that you can see that this is used and many places in the software. It would not get affected. Okay, because remember, this is a trade-off between programmability and performance. So why we say trade-off? The reason is this. Okay, so this is fine. So what if I needed as a programmer, I can demand anything, right? What if you say that, okay, fine, this would not be, I need, as a programmer, I definitely need to make sure that these two load X and load Y doesn't return 0. Just a hypothetical case, and this is probably the need for the programmer. The question is, you have a TSO system which doesn't by default guarantee any such thing. Sequential consistency, okay, fine, this is okay. But in TSO, it doesn't, guarantee such a thing. So what the programmer can do? So now, the processors that will actually support weaker model, they provide some special instruction. A special instruction such as fence instruction. Okay, for example, there is mfence in x86. But the programmer has to manually insert it. Okay, so what the fence does is that if you put a fence between memory instructions, then it will explicitly disallow any reordering, irrespective of what your memory consistency model says. But now you can see what is the programmability demand that we are now putting on the programmer or the compiler who is actually generating the code. Because wherever necessary, this ordering is necessary, they have to explicitly put it in the program. Okay. So how the the extended this reordering table actually looks like. Remember, this was what we actually had for the TSO up till this one, load store. Now we introduce mfence, and what mfence does is that it doesn't allow any reordering, whether it is with another mfence or whether it is with another a load store. It's like a barrier. You can't actually bypass each other. So what you can actually do, going back to that program that where we wanted x equals to 0, y equals to 0 not to happen, to stop it. Okay, even on a TSO machine, what you will have to do is put two mfences, because if that you put, by definition of mfence, this guy cannot actually jump the fence. That's why it's called fence. This guy also cannot actually jump the fence and go up. It is a barrier. You just stop it. You can't do it, right? Though I actually say barrier, and a lot of people actually use the term barrier, fence is a better terminology. The reason is, remember this fence, barrier typically associate with all the threads. It's a global visibility, but here, fence affect only, that particular code. If this fence was not allowed, then or was not there, then this y could have actually gone before, even though there was a fence here. So you can actually say that with these, like the x equals to 0, y equals to 0 is not possible. So you become your code becomes a now this piece of code will behave same on a sequentially consistent system processor as well as in TSO. It's just that the code get more complicated. Of course, this is a very simplistic example, but the code can actually get more complicated. So that's why you say there is a trade-off. You put more responsibility on the programmer at the cost or at the at the value of allowing more optimization in the hardware, like having a the write buffer in this case for TSO. Okay, makes sense. Any question on that? We actually covered a lot of interesting stuff. If you have any question, this is a good time to ask before we get into the weaker memory consistency models.
Sir, I'm not able to understand how a program is being like a case is being considered as a good case or a bad case.
There is no there is no consider case. I mean, I don't actually use this term good or bad case. Like, there is nothing like good or bad, or there is nothing like a good memory consistency model or bad memory consistency model. It's just a choice because there is a trade-off. And what we're talking about is that whatever your choice is, as a processor vendor, you have to declare the memory consistency model, because whether a program, multi-threaded program is correct or not depends on what is the memory, why it is running, and what is the memory consistency model of that processor. So, because some of the memory consistency model allow processor to do some bypasses, like we talked about, later load bypassing the earlier store as long as they are to a different addresses, and that can break some assumed semantics of some of the program, unless you put take extra care, like fence instructions and so on. Remember, this is affecting only the multi-threaded applications. If everything is single threaded, you don't you're not affected. Am I still making sense?
Yes, sir.
Anything else? Any other question?
Yeah, sir, are there any other way other than fence to enable SC compliant? Because let's say if we have more fence operations, that means that we are trading off the performance, right? Because it's an instruction,
True.
and then we lose the cycles, number of cycles.
Mm-hmm.
So are there any other approaches for this?
We'll talk about it. Like, there are other ways to order. We'll talk about read, modify, write instructions soon. But here's the deal: if you require more stricter ordering due to your program semantics, okay, then you are going to pay a price of it. The reason is this: like, think of this, like, if your parallel program, and then everything here is a multi-threaded program, that is what we're considering, requires frequent synchronizations. That's where you would actually be worried about these fences and so on, because again, if everything is completely like independent of each other, your you have your each thread is completely processing on different parts of the data. It doesn't matter, which means that you don't have to synchronize. And if you don't have to synchronize, how does it matter all these orders of load stores? Right? Remember that this is mattering when there are these two threads are reading same variables from two different threads or two cores. If there one set was AB, another was XY, who cares? Right? Like, I see
Got
my
it.
point, right?
Yeah.
So if your app algorithm is such that you need to talk between threads often, you have to pay a price. There's no way out of it. Oh yes, there can be different ways to enforce those ordering. We'll talk about some, but you are not escaping the overhead. A good high performance parallel program or multi-threaded programs, when they say, oh, it scales really well, what it means? What it means is that even when you increase the number of cores, number of threads, if there is little synchronization required between them, then the program will go faster and faster as you throw more threads and cores. Of course, you have to have more software threads that can run on more cores. You can have like a lot of threads, but if they're not enough cores to run, then there is no parallel processing happening, right? At the end of the day, hardware needs to execute that. But if your program is such that they need frequent synchronization, you would have to do all this. You have to pay a price. There is no escape from it. Make sense?
Yes, I got it. Yeah.
Okay. Now with this, we'll actually get into what are the weaker or relaxed memory consistency model. Now this is again in itself is a class of memory consistency model. But here, what they kind of say is that any kind of reordering between loads and stores, as long as they are to different addresses, are allowed. If all bets are off. Now we can actually say how do you write correct program on this? Can still write it by putting more and more fences. So what would happen on a program that is on a weak running on a weak memory consistency system, a processor that has actually weak memory consistency model, is that you have to put many more fences. Now you actually see, we'll go back to the story between x86 software to ARM software, right? Running the same thing on the ARM. Even if you have converted all the instructions by instruction, okay, there is a add, if there is an add instruction on x86, there will be corresponding something like that on the ARM as well. Even if you have done all of these, you might require many more fences when you are trying to run that multi-threaded program correctly on an ARM processor. Even the ARM has actually weaker memory consistency model. If you miss any of these, what can happen, then the worst thing is that this becomes, sometimes you actually tested the software, it actually ran fine because you were lucky and some of the reorderings did not happen. That would actually cause your program to fail. You deploy it in the production, suddenly the unlucky or orderings that were not possible under x86 memory consistency model show up and happens in the ARM processor, and then your program fails. Now you take that program, okay, I need to debug, you test it in your system, those unlucky ordering doesn't happen, so you are unable to reproduce even the error. Why do you actually debug? So because to debug something, as you know by this time, of course, you should have written enough software that unless you reproduce a problem, you cannot debug it. So that's the problem. So in weaker memory consistency model, you typically would allow all kind of reordering, but of course you have the thanks that you have fence, so you have to put fence instructions to make sure that your program is behaving right. Now, going back to this example, now under weak memory model, would you get R2 would be guaranteed to load 1 or not? Remember that for sequential consistency and the TSO, it would have behaved the way that a programmer intended to be. But under weak memory consistency model, think about this, all the reordering will be allowed. Would this actually return, guaranteed to return R2 equals to 1 or not? What do you think?
No.
No, yeah. So what you actually do, you have to put fences. So now, if you put fences like this, then your program will run correctly even on the weaker memory consistency model. Now you actually see what is happening. So we started with a very intuitive program, piece of program, which made sense. Like you can actually see what the programmer was intention had with this flag variable and so on. It worked fine on the sequential consistency and the TSO. As soon as I took it to weak memory consistency model, which doesn't guarantee any of the allows all the reordering as long as they are two different addresses, then you have to put this fence instruction. Otherwise, there is no guarantee. You can get lucky in some cases. Okay, this stored A might have actually shown to might have happened to the caches based on the cache hit miss and so on before this stored to flag 1, and program will run fine. You would see the same behavior between the TSO and the weaker memory. But sometimes there will be a cache miss. You don't know when it will be, and here you go, the program fails. Unless you have put fence. If you have put fence, then also irrespective of hit misses in the caches, your program will run fine. Make sense? Make sense? Okay.
Yes, sir.
Yes,
Okay.
sir.
So now we'll actually take a little bit of detour, get into the locking and the mutual exclusion, and you'll see why we are actually doing that. So you know what how to hopefully how to implement a simple locking, like simple like a spin lock, right? What you typically do, you'll actually have a shared variable, and you'll designate, okay, maybe when the variable is value is 0, then the lock is free. If variable's value is 1, then somebody has the lock. And the thread that has the lock can go and execute a critical section of the code that it needs to actually execute in a mutually exclusive fashion, and the others can actually keep on checking when this value of this variable becomes 0, right? And you can actually think of some kind of an program like this, where you are looping on a lock variable. This is kind of an taking a locking protocol, and then as soon as you get the variable to be 0, you can actually try to set it to 1, which means that you grab the lock. The thread that is able to set the variable to 1, like grab the lock. Now, it is less simple than it actually looks, because there will be complications. First of all, releasing a lock is easy. You can just set that shared variable, the lock variable value, to 0, which means that it's free. Now, taking the lock is not so easy, or acquiring the lock is not so easy, because what can happen is that you might have actually thought this piece of code should be enough to take the lock, but it is acquire the lock, but it is not. Because what can happen is that you might actually, maybe there are two threads that are actually constantly looping on this to see when this lock variable becomes 0, which means that as long as it is not 0, it is kind of looping. But whenever it actually sees this variable to 1, variable to becoming 0, that thread 1 might have gotten descheduled after that. After any instruction, a particular thread can get state scheduled. In the meantime, a thread 2 also sees that same variable to be 0, because before this thread 1 could set this lock variable to 1, it got descheduled. Right? Now, it happily takes, set this variable to lock to 1 and goes on into its business, like of executing the critical section. After some time, the thread 1 comes back and it will actually resume from where it left. The next instruction was lock variable to 1, and it thinks that it will have the lock. But now mutual exclusion is broken, because now both thread 2 and thread 1 thinks that it has the lock. Now, what is the solution to this? The solution to this problem is that you need to actually basically load this variable lock to 0 and set this variable to 1. This is actually load and store, okay, atomically, which means that there has to be an instruction that can do these two things together before it can get descheduled. So, because if it is done as a part of a single instruction, then you cannot get descheduled. You cannot actually get descheduled within the while you are halfway through executing an instruction. Okay, but for that you need a support from the hardware, which means that you need new instruction. And these are basically a class of instructions that are actually introduced in the instruction set architecture that call atomic read, modify, write. It is read, modify, write is because read is the load. It will always have a load part, and typically there will be a computation that will be actually allowed. That is the modify part, and the write part is the store part. All of this will be clubbed together. It will be done atomically as a part of a single instruction. If I give you such an instruction, you'll be easily able to implement the lock. Okay, so one example commonly used in such atomic read, modify, write instructions, or RMWs, is compare exchange instruction in x86 ISA. So this is a complicated instruction semantic. So let me actually read that to you, what it means. So this op1 and address, this actually provides a memory address. This will be a log variable address. So op1 is just an offset that you have to actually add. Okay, and what it will actually do is that this instruction would actually read this value stored in this address. This is the read part of read modify write, the load part. It will compare it with the value that is there in a specific register. This is the EAX. This is actually encoded in the semantics of this instruction. It will check only the content of the EAX register. If these values are equal, this is conditional, then it will write the value that you have provided as the op2 in this instruction in this address, the same the address that was actually just loaded, and put the flag, 0 flag to 1, so that later somebody can figure out whether this particular instruction succeeded or not, because this is a conditional. If the loaded value doesn't match with the value in the EX register, then this store part where you take the op2 and write to the address would not happen. Okay, and how do you tell that it hasn't happened? How later somebody can actually say whether this instruction could not actually write, is that by at that point it will actually set set this 0 flag to 0, ZF to 0. So you can see like these read modify writes are also conditional in the sense is that it will load, it will do some compute here it is compared, and if that succeed, then it will actually do the right part, otherwise not. And whether it succeeded doing the right part or not, it will actually keep that information in some flag. Here is the 0 flag, so that later on you can actually check it. And such read modify write instructions are compare and exchange is most widely used, but there are other too. Fetch and set, fetch and add, test and set. You can actually Google it yourself and you'll find it. But the basic idea will be same. It will be a read portion. You'll see a computation, a modify portion, and there is a conditional write after that. Okay. Now the question is how you can actually use that to create an spin lock. Okay. So here is the code. Let me read that out for you. So what it is actually doing, this is a XOR, okay, and L that you actually see, it is actually for the size of the, it is a long size of this that you are actually comparing. That is what it actually specified. So you can actually ignore that part. So what it is saying is that to register ECX, XOR it to yourself. So when you XOR a particular stream of bit with itself, what you get? What do you get? Basic digital.
0.
0. Okay. So what it is doing, basically, it's initializing the ECX register content to 0. Then it is incrementing. Last one you just ignore. L is you just ignored it. So what it means is that this value would become ECX registered value would become 1. Okay. Now this is the spinning part. Okay, now what it is doing? What it is doing is that setting the EX registered value to 0, again XOR. Okay. What it is then it's doing, this compare exchange comes in. You provide the lock address. This is the variable, the lock variable, right? Remember the EX registered value it will actually compare with, and ECX is 1. So what this guy will actually do? It will read the value out of this particular address, compare it with the value in the EX register, which is 0. If these two matches, then what it will do, it will take the value that is stored, that is there in the ECX register, which is 1. We did a XOR and then increment. It will put that in the log variable. Okay, and then set the 0 flag to 1. Right? That is the semantics. It will do all of this within the same instruction. If it is able to, then what happens? Means that it grabs the lock here. Okay, and how you actually use how do you figure out that if you have actually failed to acquire the lock? Because if this value is not 0, then you do not do this ECX. You do not take the ECX register value and write to the lock address because you have failed to grab that lock. But at that point of time, your a 0 flag would not be set. So this is jump not equals to 0 to lock entry. So what would actually happen is that it will go back here and try until it actually succeeds. As soon as it succeeds, this jump will actually fail, so it will actually flow over, which means that the lock will be acquired. And this is simply unlock, where you just take the 0 and write it to that in a lock address. This is just release. Release is simple. Now, this implementation of spin lock would work because of this atomic. Because you can think about it, you would not be able to, even if you try to deschedule, locking will actually work fine. Because this whole thing would either happen or not happen atomically. It can be halfway. Make sense? Does it make sense?
Yes, sir. Sir, I have a doubt.
Yeah, go ahead.
This is in x86, sir. So how will the same look in RISC-V?
They have a different instruction set, but they also have this atomic read, modify, write instructions. Okay, you can yourself look up those. You will actually see that there is a read, modify, write instructions, and you can actually create the corresponding code snippet for in ARM2. The basic idea is same. It's just the slightly different semantics. But the fundamental thing is that you require this atomic read, modify, write instructions.
Yes, sir. Thank you.
And how they actually, there was, I think Surya asked it, like if there is other way to implement some of this ordering. So the question is that we have seen up till mFence, right? This read, modify, writes in x86, they also has this similar behavior where RMWs across read, modify, writes, the load stores would not get reordered. So this is similar to what the fence would do. Okay. On the other hand, if there is weaker models, they might actually allow the reordering of load stores with the RMW itself. So it depends on the this depends on the particular memory consistency model. So going back to the question about ARM, in case of ARM, it's not only the RMWs, but you have to put fences as well to make it correctly work. Otherwise, there can be issues like the load store bypassing the RMWs, and you might actually get incorrect execution. Okay, makes sense?
Yes, sir.
Okay, so with that, and then what will in the the session that we'll actually have in the afternoon, the hands-on, you'll see different ways to implement these locks. You will see, we'll give you implementation, high-level implementation, pre-thread about the spin locks, and you can actually implement something like mutex, where the problem with the spin lock is that, hey, you will actually, if there are say 10 threads, all of them will be just doing busy waiting, while say there is one thread which is in the critical section. The critical section can be long, so you're wasting this spinning. Alternatively, what you could have done is that you can actually wait it, like okay, until the lock is released, you can actually wait. So that would have been a better implementation. Okay, this is the simplest implementation. You'll do exercises on that. So you'll see more about synchronizations and so on there as well. Okay. With that, we come back to the memory consistency model. So here is an insight that someone had that look, like when you are writing an multi-threaded application, what you ultimately is looking at is that you require some critical sections, some mutual exclusion, where some piece of code should execute mutually exclusively. So it should, when it is executing, so nobody else should actually execute in that piece of, in that same piece of code and so on. So basically what you require is mutual exclusion, which means that some kind of lock unlock. And if you if you if you ask the programmer to just correctly specify where is this acquire and release of locks, which means taking a lock and unlocking, if you specify that, then that the program should not depend on any other reordering of load stores, as long as you maintain the acquire release semantics. That is, like, within anything within acquire and release should be actually executed mutually exclusively with any other thread which is also trying to acquire the same lock, right? Intuitively that makes sense, right? At the high level, that is what you want out of multi-threaded applications, right? And that is what the observation behind the what we call the release consistency model. This is something that this is a release consistency model is an example of weak memory consistency model, because it will allow all load stores to reorder, and even more. What even more we'll actually see. So let us assume this is an piece of code that is actually coming from a thread. There is some load stores. There is an acquire and there is a release. You can see that within this, it should be, that's the critical section. Okay. Now, what the release consistency model observe is that, if there are earlier load stores before the acquire, if they get executed after the acquire, which means that this acquire kind of gets executed before these load stores, that is okay. That is okay, because as if there is more instruction get executed within the critical section than needed, that would not break the program, right? What should not be allowed is that any instruction load stores that are after the acquire in the program order, they should not be able to bypass the acquire operation. Similarly, if there are load stored after the release, they can happen as if they were happening before the release. But this is not possible. The load stored that were before the release, they should not happen as if they were after the release. Then you will actually break the critical section semantics. So release consistency model is even weaker than, it's a type of weak memory consistency model, but it's kind of an notionally weaker than even the typical in general weak memory consistency model that we call, because it will allow some reordering across these synchronization operations like acquire and release as well. So how that reordering table looks like is this. You have acquire release. The later acquires can bypass earlier load store, but not other way around. So if you take acquire here, load store means earlier acquire, it cannot actually bypass the later load store. This is what not allowed, right? Similarly, it's just the opposite for the release, where a later release cannot actually bypass the earlier load store. This is not allowed, but this is allowed, where later load store can go before the release. So this is yes. So this is basically what is going to be the essence of the release memory consistency model. That is, of course, I'm giving there a lot more intricacies, but this is the high level view of, say, ARM's memory consistency model. So what it means is that it allows a lot of optimizations, like we were talking about this FIFO write buffer in case of TSO, but here you can have like completely non-FIFO write buffer. Whatever happens, like it doesn't matter as long as you are consistent with the accurate release semantics that you actually need. we are out of time. So one of the things that I should actually end here with is that, this memory consistency model, we talked only from the perspective of the processor, but its memory consistency models are also language level features as well. For example, C++ has its own memory consistency model. It's called a sequential consistency for data rest free programs. So I can't actually go into the details, but the high level idea here is that so at each level, when you are talking about compiler, it is taking a high level program and it has to define for that language what are the reordering it will allow. Once it goes to the compiler, it needs to check with the hardware what reordering it actually allows and what it has actually promised to the upper level language. In the middle, it has to put, say, if the same compiler, same program, if the compiler is written right, it might be actually splitting much more fences when it is compiling for ARM versus say x86. So the compiler needs to be aware of this hardware boundary, okay, while it should be also allowed. At the programmer should be worried about what is the language level memory consistency model that one has promised. Java might actually have a slightly different memory consistency model with the C++ and so on. So that's the story of the memory consistency model. It is actually a very complicated thing, and it takes like many lectures. But this is a high-level view of what the memory consistency model is and how it actually interacts with the synchronizations. Any question? I think we are out of time by a couple of minutes, but I can take questions. Okay, I guess no question. I'll upload these slides, and if you have more questions, I'll be available during 4 to 4:30. Okay. Bye then. Talk to you guys later.
Thanks, Sarka. You'll be there, right, in the afternoon?
Yeah. So, my students will run the